I usually have a exam review for lecture 13 because why not? But thankfully we don't have exams in this class, so we'll get to talk about process scheduling instead. The one thing that we didn't talk about last time at all was real-time process scheduling and the various concerns that you have when implementing a real-time system. And so we're going to spend some time talking about that. I know. Does that power will turn off thing come on often, or should I pay attention to it? Replace lamp. All right, well, we still have another screen, so I guess we'll just forge ahead. Anyway, real-time scheduling. We already talked a little bit about this stuff. We're going to explore it in a little bit more detail today. So we have systems that are driven by specific events, and if we're talking about on the general purpose computer, almost always that's a timer interrupt because I need to draw another frame of my video, I need to play more sound samples, I need to do something like that. Maybe I need to respond to user input. But there's a lot of other real-time systems out there that have a lot of other inputs that they have to respond to. So wheel slippage in an anti-lock braking system would be a good example. If I'm running an assembly line or something like that, I may have optical sensors, I may have actual switches that get triggered at various points, or other things. Cars are getting smarter and smarter. In fact, Google has a car that drives all by itself. And so if some sensor says, hey, you should stop or you should go, then the system needs to respond to that in a specific period of time. So we call that amount of time that it actually takes, the event latency. How much does it take between the input triggering, saying you should do something, to the system actually doing it? Okay, we call that event latency. And just as a simple example, anti-lock braking is surprisingly slow as far as processors are concerned. You have 3 to 5 luxurious milliseconds before the car goes careening out of control. So the ABS system can go ahead and get around to doing that kind of thing. And of course, the other interesting aspect of this is how strict is the requirement of the real-time response. And so you may say that the real-time system is expected to meet all of its scheduling guarantees. It may not be able to, so we might actually have the real-time system say, no, I can't accept this job because I can't guarantee that it will be achieved in the specific amount of time. So it tries really hard as well as it can. Some systems are engineered so that they can't miss, and some allow events to be missed. Okay, so we talked a little bit about this. Hard real-time systems being ones that require events to be serviced within their maximum event latency. Otherwise, the system has failed and typically needs to be reset. Soft real-time systems, if we miss processing an event in time, it's not the end of the world. We just go on and, obviously, typically with a degraded performance. So there are a couple of things. We're going to talk about this whole processing thing because we've already talked a little bit about context switches, interrupt handling, blah, blah, blah. But now we're going to talk about it in the context of real-time systems. So there's two latencies that we care about. One is interrupt latency. So some pin on the processor goes high, or maybe it goes low if it's a reverse sense pin, and so now I need to start running some interrupt service routine. So what is that amount of time? We call that interrupt latency. And then there's also dispatch latency. So when I am in my interrupt service routine and say, the wheel is slipping, or some corresponding event, then now I need to switch to the process or switch to the piece of code that actually handles that situation. Some other program may be running. I need to stop it. I need to switch over to the one that should handle this event. So that's dispatch latency. Okay. So we have our tasks. This is a nice little thing, task timeline. The task is running, we get the interrupt occurring, and then we have a whole bunch of stuff that has to happen. First of all, the CPU has to finish whatever it's doing. And that could be long if we're doing a div or something like that takes a while to complete. So clearly, that whole sequence of events has to occur because interrupts are never delivered in the middle of instruction. It's always after an instruction completes and before the next one starts. Of course, if interrupts are turned off, then when I do STI, immediately the interrupts start being delivered. So that may be when the interrupt actually gets handled. So the CPU dispatches, remember, it looks up in the interrupt descriptor table. Okay, here's the address for this. It calls the interrupt service routine and begins executing. And that's going to invoke the operating system interrupt handler, which we already talked about a little bit briefly. We're going to talk about it more next time because we're going to start talking about traps and system calls. We need to save whatever was going on. So remember, we're interrupting a program, probably a user mode process, so we need to save its register state, flags, blah, 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 a few things that weren't actually saved by the processor interrupt dispatch. And so we invoke the interrupt service routine and then carry on. And so that is, yeah, so we're down one screen now. Woo! So that part is the interrupt latency. Okay, the interrupt occurs, and then the CPU goes ahead and dispatches, and then the operating system saves the state of whatever was going on. And then we're in the interrupt service routine. Now, obviously, if you're disabling interrupts a lot, you're going to have a big problem with actually getting events processed quickly. Because if interrupts are disabled, then you're not able to actually service them right away. So typically, you need to make sure that you disable interrupts for as little time as possible. That's kind of a big requirement of real-time systems. I need to always be listening for interrupts because I may need to handle it really quickly. So that's a key detail there. Also, we talked about kernel preemption. We don't necessarily require kernel preemption to implement an operating system that has real-time processes and real-time support. But if we have kernel preemption, then that makes our system even more responsive, because if we're in the middle of kernel code that's not critical, then we can go ahead and dispatch away from it. We can switch away from it and go do something that's more important and then get back to that other kernel thing when we actually have time to, when it's not as critical. So kernel preemption actually really helps a lot with interrupt latency as well. Okay, so that's interrupt latency. Now the dispatch latency, you can see we have our picture gets a little bit more sophisticated now. If you guys' necks start to strain, you can all move to the other side of the room. It won't offend me. So anyway, let's see. So we have interrupt latency, and now we're talking about dispatch latency, and we now need to switch to the process that is responsible for handling that interrupt. Okay, so that's fine. Remember, we had the scheduler and we had the dispatcher. The dispatcher needs to go as fast as possible, but we already needed the dispatcher to go as fast as possible, so that's not a big deal. And there's a few implications which are not subtle at all. So the first one, real-time processes really need to be the highest priority process in the system, because if we want to be able to preempt whatever's going on, it should be at a lower priority than whatever we're switching to. So that's why, for example, on the Mac, you have real-time processes, and then you have kernel processes are at a lower priority than real-time processes. That was something that was really key because Apple understands that a responsive system makes people happy. And so real-time processes are at a higher priority than even kernel processes. Second one, obviously if a process is running on the CPU and some higher priority process becomes runnable, it should preempt the lower priority process that's on the CPU. Okay? Again, neither one of these is really that subtle. You would probably figure them out really quickly if you were implementing an operating system with real-time support. So I should be able to preempt a lower priority process. This does not imply kernel preemption. Again, all these terms are reused in many different ways. You have threads and kernel threads, and you have preemption on a scheduling front, and then you have kernel preemption. And so just make sure you keep these all straight in your head. We're just talking about preempting a user space process. Okay? And we at least need to support that if we're going to be able to do real-time process scheduling. If we also have kernel preemption, then we're even happier. But these two things are just very basic constraints or requirements of real-time systems. Okay? Now you see that there's a missing box there. Curiously enough, why is there a missing box? We'll talk about that just now. The dispatcher obviously needs to be efficient. We already talked about that. It needs to be efficient anyway, so that's not a big deal. What's more interesting is you may have a situation where some lower priority process is holding on to resources that the real-time process actually needs. Okay? Now that's probably not likely in the computer, our general purpose computers that are sitting in front of us and so forth. But if you're talking about a system like a car that is, has some automation features, it may be that the car computer needs to stop listening to the driver and do something else because otherwise the driver will die. Things like that. So there's situations like that where you may need to grab back resources that some other process is using so that the real-time process can utilize them. And so this we sort of described as resolving resource conflicts. Okay, so if there's anything like that, then we need to handle that as well. And so you can see that all of these things kind of need to happen to get from whatever was happening to the process that's supposed to respond to the real-time event. Okay? I think this is all pretty straightforward. Are there any questions? Okay, so that part, yes. Well, that's what's interesting about it. The operating system can do whatever it wants. It can provide whatever kind of abstraction that it wants. And so it may be that if the user process was doing something, that when it switches back to the user mode process, it receives an error code or something like that saying, sorry, but your thing was taken away from you in the meantime. So you can definitely have situations like that. Now, clearly you would expect that to happen very rarely because it's pretty infrequent that a low priority process would be using the same exact resources that a high priority process would be using, like a real-time process, something like that. But if it were, if you had that situation, probably the two things would know about each other, and so the low priority process could just say, oh, I lost it because some real-time process ran, and I need to restart, I need to retry. Okay? Now that's a very specific example. There's other situations that we will actually talk about pretty quickly. We'll probably talk about them next week because one of the really interesting areas, interesting to me I should say, of operating system implementation actually comes from signal handling. How do you deliver signals to a user space process? Turns out to be really interesting to me and really sophisticated. And one of the things that can happen is a signal can interrupt a system call. So what do you do in that situation? I don't know if, now all of you have actually done a little bit of programming at this level because you wrote the command shell, but I don't know if any of you noticed that one of the error codes that can be returned by some of the system calls is e.enter. Did anybody notice that? One or two of you? So e.enter means that the system call was actually interrupted by signal delivery. The operating system will try to redo things if you have a situation where it's interrupted at a certain point. But beyond a certain point, it'll just say, sorry, I couldn't do it. Because, I was doing this one thing, and then signal came up, and sorry, I just couldn't do it. And so you could have similar situations where an operating system, if it had to handle resource conflicts, could say, yeah, you were holding it, but guess what? You're not now. and have some mechanism by which the operating system can inform the user process that it lost its resource. So you can imagine the Unix model doesn't really provide this in a generalized way. I'm not sure if Windows does because I haven't done enough Windows system programming to tell you that. The last time I did Windows systems programming was back in 2000. That was a long time ago. But you can imagine that a purpose-built real-time operating system might have a way of communicating to processes. Sorry, in resolving conflicts for a real-time dispatch, you lost your stuff, and you have to reacquire it to go on. Okay, so that's the kind of thing that would happen. All right, any other questions? Okay, let's see. So scheduling. This is where it starts to get really interesting. We're going to constrain ourselves right now to periodic real-time processes, which definitely is not all real-time processes. We just talk about what if you see a wheel slipping on an antilock braking system or something like that. So clearly there's situations where it'll be more event-driven and hopefully extremely irregular, not something that actually happens on a periodic basis. So, but you expect that real-time processes will need the CPU frequently and on constant intervals. So we say that there's some period P that we need to execute on. We take some amount of time to complete our whatever task we need to do during each period. You'll notice that I have it right at the end of the period because we're saying this is the latest that we can start it and finish within our period. And so that basically gives you this window in which the process must receive the CPU. And so we say that that's the deadline. And it's not really the deadline is really the right side of that little window. We could execute any time inside that window and still finish in time. Okay? And so if we don't finish within that window, then we're sad. We basically have not satisfied our real-time scheduling constraint. I'll say constraint, not guarantee, because we're not guaranteeing this yet. Okay. So some operating systems do require that you state your requirements, because it may be that you're not actually able to satisfy the request. And so the operating system can be clever and think about whether or not it can actually meet the required scheduling deadlines. And if it can't, then it'll just say, no, I can't do this. You'll have to try again at some point when the system is not as heavily loaded. So we call that admission control algorithms, because we simply do not admit processes that we can't have a reasonable chance of meeting their scheduling requirements. Okay? Yeah, and so this is interesting. You'll notice that second to last point, that if the OS can admit the process, it will basically guarantee that it's able to meet the scheduling requirements. Okay? So you'll see this kind of thing on hard real-time systems where you need to know that you're actually going to meet your scheduling requirements. So that's where we would have admission control. Now, even a general purpose system could have some kind of way of saying, you know what, we have too many real-time processes, performance is really going to be bad, I'm probably going to miss a lot of your deadlines, and it would be nice to be able to tell processes, you know, the system is really heavily loaded so that you could tell the user this is a bad idea. But in general, you see this primarily on hard real-time systems. Okay, so one option for scheduling processes that are real-time is called rate-monotonic. Okay? This is one of the simpler real-time scheduling algorithms. Basically, you say the shorter your period, the higher the priority is. If you have a long period for execution, so I execute every 5 minutes, I have a low priority. If I have to execute every 5 seconds, I have a high priority because I need to make sure that I get to the processor quickly. You also require preemption of processes. So if a higher priority process needs to run, then it preempts a lower priority one, and so forth. And we're not going to prove some of the assertions in this lecture. I will point you at other material where it's really interesting. But as far as static priorities are concerned, this algorithm is the optimal algorithm for scheduling real-time processes. Like it says here, if a set of real-time processes can't be scheduled by this algorithm, then no algorithm with static priorities is able to schedule it. Okay? Now, there's kind of an interesting hedge here that you'll notice. We have static priorities, so rate monotonic, we just say shorter the period, the higher the priority, and that priority is fixed. Obviously, it varies based on the period, but that's the only thing that it varies on. And you'll also notice that no other algorithm that assigns static priorities can do better than this algorithm. So that should be a huge hint. Well, maybe there's a giant part of the picture that this kind of algorithm where we only assign static priorities is incapable of handling. We'll talk about that in a second. So low priority processes can be preempted by higher priority ones. So you can have priority inversion with this, which is kind of interesting, but we're not going to go into those kinds of situations, thankfully. So the real question is, can you actually schedule a set of real-time processes? So we say that they have a period, and they have a certain amount of time that they take. We call that T. and it's a CPU burst, obviously, because if we have to do I/O, then the process is going to block anyway. But it needs to perform some CPU burst of a certain length during each period, and then it will have met its deadline. So here's our example. We have two processes, one with a period of 50 clocks and the other one with a period of 100 clocks. And P1 has a CPU burst of 20 clocks, and the other one has a CPU burst of 35 clocks. Can we schedule these? Well, thankfully we can just sort of simulate this in slideware, and we'll see. So you see P1 has to execute on a certain period. P2 has a period that's twice as long, so it executes half as frequently. P1 has a higher priority than P2. So they can start executing at the same time at the beginning. And again, this is where you notice that, okay, we had our deadline and it was a window. So what we're going to do here is we're going to start executing as early as we can within our window to try to get done as soon as possible so that we have no chance of missing our deadline. So anyway, P1 and P2 can start executing at the same time. But who gets to go first? P1, because it's the higher priority. So it runs. And remember, it had a CPU burst of 20 clocks, so it goes ahead and finishes. So then P2 starts, and it takes, how many do we have here? 10, 20, 30. But you'll notice something interesting. Remember, it takes 35 clocks to finish. But at the time we hit P1's deadline, then a new window opens for P1. So P2 gets preempted again before it actually finishes. Okay? And P1 finishes because it only takes 20 clocks. P2 is then able to finish its task. Are we happy so far? Yeah? I mean, at least in the context of scheduling we are, right? So P1 has been able to run twice in 2 periods, so that's good. P2 has been able to run once in 1 period. Everybody's met their deadlines. We're happy. And so this mechanism, this process can just repeat itself again. P1 runs, finishes, P2 starts to run. In the process of P2 running, it's P1's turn again, so it preempts P2. It runs to completion, then P2 finishes its last little 5 clocks of CPU burst, and everybody's happy. We meet our deadline. Right? Everybody with me? Okay. So you can see that we have time left over. So you might say, hey, you know what? We could either add more processes, or we could go ahead and have longer CPU bursts for these things. We have a couple of different options. So we can actually quantify this as the CPU utilization. So we just say, how much time do you require over what is the period? And so you can see here that P1's CPU utilization is 20 clocks over 50 clocks, or I need 20 clocks out of every 50. And so you can say that I need 40% of the CPU time. So that's the CPU utilization of P1. Do the same thing for P2. I need 35 clocks out of every 100 clocks. So my CPU utilization is 35%. Now, presumably, we can't get over 100% CPU utilization, right? So 0.4 plus 0.35 is 0.75. That's definitely less than 1. So we should be fine. So the question is, can we actually use our CPU utilization to tell if a set of real-time processes can or cannot be scheduled? Okay. Add up the CPU utilization of all of our processes. If it's less than 100%, then yay, we can schedule it, right? That's the idea. Well, we take another example where, again, we have P1 taking, well, actually, you can see now that P1 takes a few more clocks. Now it takes 25 instead of 20. And it still has a period of 50 clocks, so that part at least is the same, but it has a slightly higher CPU utilization. P2 now has a shorter period and the same CPU utilization. So now P2 is, I'm sorry, not CPU utilization, the same CPU burst size, because its utilization is actually going up. I have to be careful about these terms. So P2 has a period of 80 clocks, and it still takes the same CPU burst. So these are our deadlines now. P1 has a deadline at 50 and 100 and 150 and so forth. P2 has 80 and 160 and 240 if we drew that, but we don't. And again, we compute the CPU utilization. P1's utilization is 25 clocks over 50 clocks, or 0.5. And P2's CPU utilization is 35 clocks over 80 clocks, so that's around 0.44. You can pull out your calculator if you want to see the exact amount. And so we see that the CPU utilization is actually under 100%, so we think, yes, this is good, I can do it, right? But this is where we start getting sad, because if we actually tried to do this in a real system, we would start to notice that we will fail. It is not possible to execute these processes and have them always hit their deadlines if we use rate monotonic scheduling. So again, fixed priorities for these real-time processes. So again, we simulate it in our slideware. So P1 and P2 can both run at the same time. So P1 gets to run first, and it runs, and it obviously meets its deadline. P2 gets to start executing. But then we enter P1's window again, so P1 preempts P2. After P2 has only run for 25 clocks here, so we still have another 10 clocks that we have to complete. So P1 runs, P1 is happy, it runs to completion because it's highest priority, and it's going to hit its deadline. But now notice we only have 5 clocks left to get 10 clocks of work done. So P2 is going to miss its deadline, which makes us sad. Okay? Well, I mean, I suppose specifically it makes P2 sad. Okay, so it's interesting that in this situation, even though we have a CPU utilization that's less than 100%, we still can't guarantee that these processes will all hit their deadlines using rate monotonic scheduling. Okay? This is a pretty interesting result. And it was actually quantified. There were a couple of people. Let me go ahead and throw this up here in a second. But there was a paper that was done by a guy at MIT and another guy at JPL, because obviously JPL cares a lot about being able to schedule real-time processes for spacecraft. So if you have n real-time processes, the CPU utilization has an upper limit that is not 100%. And this is the specific expression. So n times 2 to the 1 over n, or I guess just what, the nth root of 2, minus 1. And so for two processes, the utilization has to be less than 0.82, which you will notice was, our first example was below that. It was 0.75, so we knew that we could hit it. Okay. For our new one, we have 0.94, and that's definitely higher than the limit, so we cannot schedule it using rate monotonic scheduling. And if n gets large, the CPU utilization goes down to about 0.69. Where if you have a CPU utilization larger than that, then you can't schedule all those real-time processes. Which is wild, because what we're basically saying is our CPU must sit idle for at least 30% of the time if we're going to schedule all our real-time processes correctly. Okay? Or for two processes, the CPU has to sit idle at least 82% of the time if we're going to be able to schedule our real-time process. That's kind of wild. So the specific paper, if you want to look it up, scheduling algorithms for multi-programming in a hard real-time environment, way back in 1973, before any of us here were born. They had figured this out. Okay, so that's rate monotonic scheduling. And like I said, it is the optimal algorithm, or it is an optimal algorithm for static process priorities. Earliest deadline first is a different algorithm. This is actually the one that we talk about in CS24, and there's kind of a reason why. Basically, we set process priorities based on how close their deadline is. Whoever has the closest deadline has highest priority because they're in the most danger of missing their deadline. Okay, this is the way that students schedule completion of homeworks. Probably not a good idea, but anyway, it's a really interesting algorithm because it actually doesn't suffer from this limitation of rate monotonic scheduling. Okay, so processes have to state their deadlines to the scheduler. And this is the same example as before. So P1 has a period of 50 clocks, CPU burst of 25 clocks. P2 has a period of 80 clocks and a CPU burst of 35 clocks. This diagram gets a little bit more complicated. I apologize. It's just hard to draw. So you have P1 and P2. These are their requirements. And so P1 has the earliest deadline. Remember, P1 and P2 are both in their window. They can both run, but P1 is closest to its deadline, so it gets to run first, and it completes. Now P2 starts running, and we hit the point where P1's window opens again because we passed 50 clocks, and now P1 has to finish before we reach 100 clocks. But now we have two processes, P2 for its first deadline and P1 for its second deadline. So you see that P2's deadline is still closer. So P2 is still higher priority at this point. So it gets to run to completion. P2 is now happy. It's like, I've hit my deadline, yay. But we're still inside P1's window, so P1 starts executing. Let me see if I have this. Yeah, so P1 starts executing because P2's deadline is now way off at 160. P1's deadline is 100. So P1 runs to completion. P2 again begins running because we're in P2's window. So we're trying to get work done before we hit clock number 160. And then we enter P1's third window. Now, where does P1's third deadline sit? 150, right? So we have 160 for P2, we have 150 for P1. P1 should now be highest priority. So see, we enter P1's window, but P1 is closer to its deadline than P2 is, so we can go ahead and preempt P2 and start running P1. So P1 runs to completion for its third deadline, and then P2 gets the processor back and runs until it completes. Because we haven't actually, so P2 gets to complete before it actually, before P1's window opens again. All right? And so forth. Once you finish here, P1 will run next because P1's next deadline is 200. P2's next deadline is 240. So P1 gets to run next and it'll run to completion and so forth. You can sort of just imagine how this will all play out. Okay? Any questions? But you can see the earliest deadline first changes priorities based on who's closest to its deadline. And we've already demonstrated that this is superior, at least in this specific case, to rate monotonic scheduling, because it's able to schedule something that the other one wasn't able to. But that's what's interesting about it. Okay, like I say here, it doesn't actually have the same requirements as rate monotonic. Rate monotonic required that we actually have periodic processes. This one we really only require that processes say when they need to run. So that could be, I just need to run at this point as a one-shot. Or maybe I need to run at this point and then I have another deadline a little further out and then I have another deadline a little closer. So you could state those kinds of requirements and you could use earliest deadline first scheduling to handle those situations. Okay, so that's kind of neat. Also, earliest deadline first is theoretically optimal, which means that if you have a set of processes, set of real-time processes, whose CPU utilization is, you sum it up and the utilization is under 100%, it can schedule it. Yay! So that's already way better than rate monotonic scheduling. Of course, we had all those other things that have to happen when we get a real-time event and we have to dispatch, so that is overhead. And that imposes a limitation where we typically can't actually achieve 100% CPU utilization. Remember that CPU utilization is computed from the process behaviors, not from all of this dispatching as well. So this is the most obvious example where all of these other details are overhead for the operating system. Okay? But it's pretty neat. Any questions? Any questions on real-time scheduling? This is all that we're going to talk about with real-time scheduling. You may be happy to know that it never makes an appearance in CS124 beyond this lecture. So it's not something that you have to implement, but it's kind of nifty stuff. I think it's really neat. And it's really interesting that you have these various approaches, and they have these subtle limitations that are not obvious at first. And you kind of have to tinker with various scenarios before you really are able to discover and quantify their limitations. We'll see similar issues when we get into page eviction policies. It turns out that certain page eviction policies have unusual characteristics, and then other ones don't have those characteristics. And so there's kind of categories or classes of solutions with different strengths and weaknesses. So we'll talk about this kind of thing again in the future, but this is basically all we're going to talk about when it comes to scheduling real-time processes. Okay, last two things that I wanted to talk about today are actually, I don't know if it's right to say, yeah, I think it's right to say two things. We're going to talk about two different schedulers used in Linux. Okay, one of the things about Linux being developed by engineers all around the world as an open source project is that you see a lot of experimentation, and typically it's a very good thing because you get to explore ideas and whether or not they're good. And so Linux 2.4, we'll start there because you have to understand the Linux 2.4 scheduler before you get to the current scheduler. But basically time was divided into epochs or epochs, depending on how you like to say it. It's kind of like tuple and tuple. So I like to say epochs now, but that's probably not entirely correct. Whatever. So basically at the start of each epoch, you have priorities assigned to all of the processes. Okay, and those priorities are based on previous behavior. So real-time processes obviously are going to be the highest priority, and those are absolute priorities because we need to make sure that they stay high priority. Interactive processes have a dynamic priority based on how they behave. So I'm relinquishing the CPU all the time. I'm getting blocked on I/O all the time. Good, you get to have a high priority. And then batch processes or processes that get preempted all the time. It's like, get off the CPU already. Then those are the ones that get the lowest priority. And the Linux scheduler would compute a time quantum for each process based on its priority. Okay? And so basically, the higher the priority, the larger your time slice was, which is kind of interesting because you kind of think, okay, these batch processes or compute-intensive processes probably should have a large time slice since they're low priority. But basically, when you use up your time quantum, you're preempted off the CPU, and the scheduler decides what to do with you. So that's the basic idea behind the Linux scheduler. You can see it's kind of like some of the things we've seen. It's kind of like priority scheduling. Kind of has similar characteristics to multi-level feedback queues. So this is what would happen. The scheduler would iterate over all the processes that were on the system, and it would compute some goodness metric, which is kind of interesting. It was just some heuristic that the engineers came up with to say, this is how good we think you are. Okay? And I have this interesting little note here. If you had a process that had previously run on the same CPU that the scheduler was now running on, you got a little bump up in your goodness. Why would that be? Well, probably because there's some of your data or some of your code still in cache. So if I switch back to you, the system will probably run a little bit faster. So you get a little bonus in your goodness. Okay? And so whatever the best process was, the goodest one, would get the CPU and it would get to run. Okay? And so part of that was obviously the priority of the process. And so if you have a high priority process, its goodness is going to be higher than some batch mode process. And so it would get to preempt other lower priority processes, and it would go ahead and get the CPU. Okay? And you can see that you have preemption as well. Now basically this would happen where all the processes would run. They would each one use up their time that was given to them. So that means all the high priority processes, they'd have a big time quantum. They would get preempted all the time, so they'd run, they'd do their little CPU burst, and then go back to blocked, and then they'd run again, and go back to blocked until all of their time quantum was consumed. The low priority processes would run and probably have to be preempted at the end of their time slice, and then they'd be bumped off the CPU. So all the processes get all of their time, and then the current epoch is up. Okay? So you'll notice that a process can be scheduled multiple times on the CPU. I'm a high priority process, I get preempted a lot, I get on the CPU a lot. Okay? No big problem there. If I'm a low priority process and I get preempted by high priority processes a lot, well, that's okay. It'll eventually come back to me and I'll get to run a little more, and when my time slice is up, then I have to wait till the next epoch. But you can see that processes would get to hop on the CPU kind of frequently, which is an unusual characteristic of the Linux 2.4 scheduler. So what happens at the end of the epoch? Well, we go through and compute goodness for everybody. We compute everybody's priority. We update everybody's priority. So you were high priority and you've been preempting a lot, or you used up your time slice a lot. You didn't actually do a lot of I.O., so your priority gets decreased. So now you are going to be less good. You're now a slightly bad process. Okay? You have some batch process or compute-intensive process, and it starts blocking on I.O. a lot. Then you say, you know what? You should get a little bit more goodness. And thereby, you'll also receive a larger time slice. Things like that. So this is what would happen at the end of each epoch. And so what they noticed, and you could probably notice this yourself if you just think about the problem a little bit, is that you've got all these sweeps through all the processes. At the end of each epoch, I have to go through all the processes and recompute a priority for them. Every time the scheduler runs, I go through all the processes and figure out which one is goodest. And then I run that one. So this is kind of lame. And you could see that this would not scale very well as you get a large number of processes. So the Linux 2.6 scheduler was completely rewritten. It would still use the 2.4 approach, but it was rewritten in a way that would make it as efficient as possible. And so we ended up with the O1 scheduler. Whoever creates these schedulers clearly has a gift for naming them, because you think, O1 scheduler, wow, that's got to be the best possible scheduler. So that must be one that we want to use. Okay? But now, instead of actually doing these things in a very formal, let's go over all of the processes at once, it's now sort of done in a more incremental way. So now we have a priority array, which is very similar to our multi-level feedback queue mechanism. Okay? Each priority level has a queue of processes. You can see the highest priority, or I should say the second highest priority has 2 processes at that level. The fourth from the bottom has 2 processes as well. And we also have a bitmap that tells us which queue has processes. So that we don't even have to look through, like iterate with a for loop over our array of priorities and say, okay, do you have a null? Do you have a non-null? Which one is best? You can just use the bitmap to figure out which process, I should say which queue has processes in it to start running. So that'll be a little bit, you use your bit manipulation magic to figure out that. Okay? And so basically finding the highest priority process to run is a constant time operation. Now it would still be constant time if you have a for loop, because you're looking at the priorities. You're not looking, you're not iterating over all processes. So you have a fixed number of priorities, and so you're still going to have a constant time operation. But you can even make the constant better. It's like, if we say it's order n, then it's still constant times n. So let's make the constant smaller, and we're happy. So we try to find the index of the lowest one in the bitmap, and then use that to access our priority array. Okay, seems fast so far. There's 2 of them. Okay, we have the one for the current epoch, and then we have one for the next one. And so the active array is going to be processes that still have some of their time slice left. And then the other priority array is processes that have consumed their entire time slice. And so when we have a process consume its entire time slice, you can probably guess exactly what happens. We move it to the expired array, but we also compute its new priority. So it just goes ahead and slots over into the new place. Okay? This guy maybe stays at the same priority. I don't know why I animated this all, but there you go. Okay? Yay, slideware. Okay? So you can see that we're sort of doing this incrementally. We're spreading out the cost instead of doing it all at once in a very inefficient way. When the active priority array is empty, our bitmap becomes 0, then we know that our current epoch is over and it's time to switch to the new priority array that we just built out. Okay? Because now expired becomes active, active becomes expired, and off you go. Okay? So, same approach as Linux 2.4, but written in a much more intelligent way. Okay? And so that stuck around until Linux kernel 2.6.23, because I know you probably care about that number. We're already like up to what? I can't remember what the current Linux kernel is, but we're way past that now. But yeah, the problem was that the order 1 scheduler was still really kind of convoluted, and there were a lot of parameters, like what should be the minimum time slice that we give to batch processes, what's the maximum time slice we give to interactive processes. There's this weird relationship. If I give batch processes too large a time slice, then all my interactive processes start to stutter when their time slice runs out and the batch process gets to run for a really long time. So there's all these little weird things that you have to tune for the O1 scheduler. And so people didn't like it. There would always be, somebody says, well, let's make this little change, and then all the interactivity tests on Linux would just dive because they thought, okay, this is, seems like a reasonable change, but then it was sort of very unstable, and you couldn't always predict the results. And so if there was a scheduler name that was better than O1, it would be completely fair scheduler, right? Okay, this should be the last scheduler we ever used because obviously every other scheduler was not completely fair or something. So, but anyway, now we have the completely fair scheduler in Linux. And I think it may actually still be used. I'd have to look that up. But the completely fair scheduler has a very different approach to how processes are scheduled. Okay? And you'll see this notion of a fair share described a lot when you read about the completely fair scheduler. Basically, that's dependent on the process's priority. Okay? So if I have a high priority process, it should get a larger share of the processor. If I have a lower priority process, it should get a smaller share of the scheduler. I mean the CPU. Okay? So what happens is each process has a virtual runtime. You guys already have your timers and stuff. You can imagine in your Pintos kernel thread implementation, every time you switch to a kernel thread, you start counting how much time it gets to run. Okay, so that's an actual system clock saying this is how much time the process has run for, and you can update that relatively easily. I don't think you have to do that. It may already be taken care of for you. Maybe it's not because your scheduler doesn't care. But yeah, so that would be the way that that's done. But the virtual runtime is a little bit different. It's not the actual system time. Basically, the virtual clock is scaled so that higher priority... This is wild. It's like relativity in the operating system. The higher the priority of the process, the slower its clock runs. The lower the priority of the process, the faster its clock runs. So that lower priority processes run out of time faster than higher priority processes. Okay? So that's pretty wild. Now, the other thing is that since a high priority process is going to be preempted a lot, its virtual clock is also going to run slower because of that. So I'm running, my virtual clock is moving, I stop running because I do something that blocks, and now my virtual clock stops running. So my clock keeps staying really slow. Now you have all these processes that are ready to run, and they each one have a virtual clock that's ticking up from 0 when the process was started. And they're maintained in an ordered tree. So that the bottom left process always has the lowest virtual clock. That's the one that gets to run. Like I say here, it's log n to insert a process into the tree, so it's not as good as the O1 scheduler anymore. But anyway, that's the one that's run for the shortest amount of time, therefore it should get the CPU first. That's the notion behind the completely fair scheduler. Any questions? They seem to like it. It seems to do pretty well. Let's just wrap up our discussion pretty quick. So obviously when you have some kind of tree structure and you want to keep track of something that's way down deep in the tree, well, there's easy ways of keeping track of that so that you can actually hold that in a separate variable, and then it becomes very easy to look it up. So, so that's O1 for looking up a process to run, but when you modify the tree, that's typically a log n operation. So yeah, time quantum is based on the targeted latency. So this is the other thing that's really interesting. The time quantum is sort of picked system-wide. So the targeted latency of the system, how quickly should every process get the CPU? The total number of processes in the system, which obviously if the total processes goes up, each process should get a smaller slice, but then you have a minimum amount that everybody must get. And so basically using that global thing, that global time slice size, and everybody's virtual clocks, where everybody's clock runs at a different rate based on the process's priority and how often they block, that's how the Linux scheduler decides who gets the CPU next. Okay. So here are the general behaviors. So processes blocking or yielding frequently, they have lower virtual run times because they're not getting to run. Their virtual clocks aren't progressing. And so they end up leftmost most of the time because their virtual clocks are very low, and so they get the CPU really quickly. So that's a good thing. If you have a process that's running and completing its time slice all the time, well, its priority is going to stay low, and so its virtual clock is also going to be very high. It's going to run faster, so it'll be at the right side, and it will be preempted by higher priority processes that become ready to run. Okay, so that's kind of an interesting thing. I love that people are experimenting with this kind of stuff. So just keep that in mind. Linux is a great test bed if you have interesting scheduling ideas that you want to experiment with. And I believe that they also have a pretty good test bench for measuring process interactivity and process responsiveness so that they can, because if they're experimenting like this, clearly they need some way of actually quantifying whether it works or not. Okay. Anybody have any questions? Alrighty, so just as a last thing to mention, Stride scheduling, I'm going to give a little shout out, I guess, to Stride scheduling, which you may or may not have seen on a CS24 exam. I like Stride scheduling. I like lottery scheduling are both really interesting, different approaches, so there's a paper about that. And what we'll do next time is start talking about system calls to get ready for the 4th project. So we'll see you all next time.